Hello and welcome. This is now lesson number 8 about the very basics of computing. And this is going to be the last lesson in this series of lessons in which we have studied mainly this imaginary computer and machine instructions, and we have studied how programs are executed on a machine level. And so we have now studied the very basics. And if you want to study something more, we can take a look at the natural programming site. So I go to naturalprogramming.com and I see 8 start page. So there you will find this link to full documentation of the imaginary computer. So there are still some programs are there explained in those chapters. If you want to study them, you can do so. I have actually the document open here, so there is one section in the document called programs that use the keyboard, memory area and stack. So that is this section of the book or the chapter. It shows how we can read the keyboard of the imaginary computer, and how we can then store numbers in memory, and how we can store numbers in the stack. So if you are interested, you can study that, but if you feel confident that you understand how machine instructions work and how the main memory works, then I think it may not be necessary to study this. So you can then start studying high-level programming languages. And in this simulator, if I again activate this simulator, so in the simulator there are also built-in programs that are not explained in the book or in that chapter that I showed you. So you can find programs like, for instance, there is this program called multiply2sums.iml. So I loaded it into the main memory, and if I put the simulator to full speed and I start executing it, so it is a very long program there that shows that how we can then first add numbers and then we can multiply those numbers. And that shows that multiplication operations can be done also without having any special instructions for that in the processor. So this particular program, it runs really long, and if you put this to the, if you select this binary numbering system for the display, you can see this will show that how computers inner workings of computers look like. So if your friends or if your mother asks that how these computers work, then you can maybe show this thing, and I think it looks a little bit impressive. So this shows that it's with this simple processor it is possible to do rather long calculations and many things, and so this imaginary processor is really operating like a real processor. But of course, real processors, they are much more complicated, as I said in the beginning, so that they have bigger main memories, they have more registers, And of course, the main difference between a real computer and this imaginary computer is that the all the registers inside this computer or the processor, they are 8-bit registers, which means that they can store only 8 bits or 1 byte of information. But in real processors, they can be 32-bit processors nowadays, or they have been 16-bit processors, or there are even 64-bit processors, and that means that all the basic unit of information in those processors, it is then 32 bits or 64 bits, for instance. So this is the perhaps the main difference between the imaginary computer and the real computers. And in real computers there are more machine instructions, more special instructions, and things like the instruction fetch operation can be more complicated than in this imaginary processor or computer. So now it did the calculation, and you can see that it made 2 adding operations, and then it made 1 multiplication operation, and it could produce this result of calculation. But of course that we can't multiply very big numbers with this computer, because the largest number that can be stored in the registers is 255. In real computers, their registers can store much more larger numbers. And of course, real computers, they have also so-called mass memories like disks, and this has only the main memory. But the operating principles are the same in real computers and also in this computer. So we could then take a look at this or study a little bit what higher level languages are. So I have actually written here an IML program here. Or actually I will take this, let's take this out. So now I have an IML program here. It's called SumVariables.iml. So I'm showing here that with this IML language you can specify variables or reserve memory like this, that you give some address name and then you use the name constant, or you use the name data there. And if you use a name constant there, it reserves 1 byte of memory, and it initializes that 1 byte with a certain given value. And for instance, this variable is now initialized with value 3, or this variable has 1 byte that is initialized with value 9. And then there is one variable here that has not been initialized. This just says that we reserve 1 byte of memory here. So what this particular program does here, it first sets the memory pointer to point to some variable, and it loads then that value from memory, and in practice it loads this value 3, and it then sets the memory pointer to point to another variable, this one, and then it loads the register B from memory, and then it loads this value 9 to register B. And then it has this instruction add register B to A, which means that now the value that is in register B is added to the value contained in the register A. And then it sets the memory point to the third variable, sum of variables, and then it stores the register A to memory, and then it stops processing. So I have actually compiled this program, and we could take a look. We could take a look at the compilation result. So I have it already here. So I just compile it with the command that we have seen, and then it produced this file somevariables.ice, which contains the machine instructions, and then I have displayed this file somevariables.ice, and it shows these numbers are now the machine instructions. So what I'm going to do, I'm going to copy these. I'm going to write these values to the main memory of the imaginary computer, and then we will then see that how it executes them. So I reload the simulator, and then I press this modify button, and I will quickly write these values to the main memory. So 21 or 21, 0b, 28, 211, 0c, 2c, 12, 21, 0d, 26, B2, and then there's 3 and 9 and 0. So that should be the program now. So actually with this translate button I can verify that the program is more or less correct there. So it seems to be quite correct. I press the reset button and then I execute it. It doesn't display. I will execute it in full speed. We can just see. So what actually happened here? Earlier there was these values 3, 9 and 0 there in the main memory. So these are the values of the variables, and now there is the last value is now, it's changed from 0 to OC, and this OC is now the sum of these two numbers. We can check it in decimal form. So this is now the value, the sum of 9 and 3 is 12 in decimal system. So we did see that it calculated the sum of the two variables, as was the name of the variable there, so that there was this. The last variable was like a variable where the sum is stored. So what we saw here is that with this instruction we can calculate the sum of two variables. So what I'm going to do now I'm going to write it here in the same file. I will take it out later on. So that what this would mean if the above or this calculation would be done with some higher level programming language. So, for instance, languages like with a language like C. In C language, for instance, there is no C language compiler available for this imaginary computer, but if there were, it could be the corresponding C program. If we think that this is now the IML program, the corresponding C program would be like this. So we would reserve the or specify the variables in the following way, so that we would say int, which would mean an integer variable, and then I would write a name, and then I would initialize it with value 3. And then I would write another or specify another variable. So this is the name, and I would initialize it value 9, and then I would have the third variable sum of variables, and I wouldn't initialize it at all because we do the calculation with it, or the calculation result will be stored there. So, and in the C language I would do the summing of the two variables in this way. So this would now be if there would be a C, or if there were a C compiler for the imaginary computer, these kinds of program lines would correspond to these program lines in IML. And what we can see here, first thing is that we can see here that writing the same thing in C, a higher level language, results in less program lines. So here we have 1, 2, 3, 4, 5, 6, 7, something like 10 lines of program, and here we have only 4 lines. So that with the C language, or which is a higher level language, it is possible to describe the same thing with less writing. So that is one reason why we use so-called higher level programming languages in this world. So that's very important, and then the one thing is also that is important is that we don't, in the C programming, or these lines could be in a Java program or in C# program, for instance. But with the higher level programming language, we don't need to think about the process or registers or anything like this. We can just think about the mathematical thing. So here we just think about that we first do this mathematical operation. We calculate the sum of the contents of the two variables, and then we store that value to this third variable. And we don't need to, when we are working with higher level languages, we don't need to think about the how many or what kinds of registers the processor has, or what kinds of machine instructions the processor has. And yet the result would be the same, so that if this would be compiled, then if we had the C compiler for this imaginary computer, so it would produce machine instructions that would look like these. So that this is the reason that, or these are the reasons that these high-level programming languages have been invented, so that we don't need to think about the internal structure of a processor, and we can make things happen with less program lines. And also one important good feature in these higher level programming languages is that with this, if I have some program, I could take these program lines and compile them in some other computer, and they would work also there. But when I write programs like these, they can be only executed in the imaginary computer. So a language like the IML is a special language for this one processor, but this language like C is a more general purpose language. And so that is the reason that why you should in the future concentrate more in programming with languages like C or Java or other high-level programming languages. Yes, so I think that I have now said the most important things related to the very, very basics of computing. So after these lessons, you should understand what are machine instructions and how processors work and how programs are compiled and things like that. And I think after this you could start studying some higher level programming language. So this was the last lesson in this series of lessons, and I wish you success in your programming studies. So thank you and